Hello, and welcome to 3.5, Limits at Infinity. So, we've talked about infinite limits before, but limits at infinity, this is as x goes to infinity. And it's either plus or minus infinity because, we go to both sides. We don't discriminate. So, as x goes to infinity, we're trying to determine what happens kind of at the end of the graph, right? At the far right end. And as x, x is going to negative infinity. I can't do that. X is going to negative infinity on this side. So we call this the end behavior of a function. What happens at the far left end, at the far right end of a graph? The limit as x approaches infinity means the limit as x increases without bound. Okay, not the y values. Earlier we talked about what happens as x approaches c and the f of x goes to infinity. That's an infinite limit. This is now a limit at infinity. So remember, it might be math, but words matter. Okay, so what happens? Let's take a look. Let's use our calculator here. And take a look at our chart example. Let's take a look at the function that is 6x squared plus 5x all divided by 3x squared minus 9. Oh, I forgot a parenthesis here, so I'm going to go back. I have to tell my calculator. You have to be smarter than your calculator. You have to tell it what you want it to do, so I have to put the parentheses all around that denominator or else it's not going to graph right. And I don't really care about the graph. I mean, I kind of do. But what I really want to know is if I can make this graph extend forever, what happens to this line? Where does this line go? And we can do that by looking at our table. And I'm going to set up our table first. We're going to do an ask. So we're going to move down here, click over on ask. And then I can go to my table so I can input my x values. So when x is 10, we get let's just write this down. We get 2.2337. 10 squared, that's 100. 2.0173. 10 to the third, that's a 1 followed by 3 zeros. Because I can count 3 zeros. And 10 to the fourth is a 1 followed by 4 zeros. We'll look at that. 2.0017 and 2.002. It looks to me like this limit is becoming 2, right? The larger and larger our x values, our inputs get, at least in the positive direction, because that's where we're going, we end up with positive 2 as our overall limit. But check out if we go to negative infinity. So I'm going to come back up here. It's the exact same function, right? Same function. A and B, I'll change that maybe to a B there. Let's go with minus 10. I get 1.89. What if I do minus 100? 1.98. Minus 1,000. 1.9983. And the last one, negative 10,000. 1.9998. So let's call this B. Notice, all right, these are decimals, not commas. The limit from either side is 2. All right, one's coming down on 2 and one's coming up to 2. Hey, my dogs are about to go nuts. I'm going to hit pause. And so if I'm in a different place when you come back, I promise you haven't missed anything. Okay, I promise you didn't miss anything. There was the chart example we did. Okay, now horizontal asymptotes occur when the limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And that's exactly what we found here. Right? The limit as x approaches infinity of this function is 2, and the limit as x approaches negative infinity of this same function is also 2. That means here, find the horizontal asymptotes, if any. I'm going to write y equals 2 as our horizontal asymptote. Remember, it's always the equation of a line. It's a variable equals a number. And in this case, since it's a horizontal asymptote, it has to be y equals L. Okay, there can be almost 2 horizontal asymptotes, one to the right and one to the left, or one from the positive side, one from the negative side. Don't make it harder than it needs to be. All right, now, sometimes they just kind of have natural little bit of difficulty. If we're finding the limit as x approaches infinity, it looks like this is 5 minus 0. But when it comes to arithmetic, I would not do it like this. I would instead simplify 5 minus 2 over x squared to be 5x squared over x squared minus 2 over x squared, 5x squared minus 2 all over x squared. And this limit, turns out, is easier to find. In fact, we could use our tables if we wanted to. We could do the same idea with a table. In order to find this limit happens to be 5. Or, check it out. Once we write this as a rational function, I am so sorry. I put a mint in my mouth so that I had enough saliva to continue talking. And it's banging around on my teeth. I apologize if the microphone's picking that up. Where there's a rational function, right, and the powers are whole numbers, if the bigger power is on top, the limit is infinity. It's an infinite limit at infinity. If the same power is on top and bottom, here 5x squared, here's 1x squared, same power, top and bottom, the leading coefficients, 5 divided by 1, is our limit. If the bigger power is on the bottom, the limit is equal to 0. Check it out right here. We found the limit as x approaches infinity and the limit as x approaches negative infinity of this function was 2. Same powers, 6x squared divided by 3x squared, 6 over 3 gave us our answer of 2. So we see this in pre-calculus, but now we have the basis for it, the reason behind it here with calculus. All right? A lot of that stuff we just kind of tell you before. Well, it's because you don't have the calculus to know why yet. 5x cubed minus 3 over x squared. And I got to tell you right now, that's not going to work for me. That's coming over here. 5x cubed minus 3 over x squared. If I want to find the limit as x approaches infinity, 5x cubed over x squared, essentially this all becomes, it's like the same as the limit as x approaches infinity of 5x when we divide, and that will be infinity. Let's do another one. Let's look at the limit as x approaches infinity of 5x cubed minus 3 over x squared. That's an x cubed, because I can read. This is essentially the limit as x approaches infinity. Everything else is kind of just unnecessary. And we get a 5. Some leading coefficient action here. And the last one, as x approaches infinity of 5x cubed minus 3 over x to the 4th. Notice that as x is going to infinity, our powers, this x to the 4th is bigger. So it's like we have 0x to the 4th over x to the 4th. And that's 0, right? X cubed, that's a smaller numerator than denominator. In order to make them equal, we could add the 0, x to the fourth, and if we have a 0 limit. So I'm going to put a 0 over here. All right, so just because we're in a higher level of math doesn't mean any of the properties you learned before are wrong. They're exactly the same because that's how we roll. And so remember that from pre-calculus. Now you just happen to know why. When the powers are not whole numbers, so they're radicals or fractions, we're going to divide both the top and the bottom by the biggest power of the denominator. You're going to simplify and then reevaluate. Okay, so 3x minus 2, that's no big deal. I'm looking at this. And we have the square root of 2x squared plus 1. Our highest power is the 2x squared. But really all I care about is the x squared. Right? The highest power of x. Okay. But the square root of x squared, that's the same as x. Right? It's actually the absolute value of x. But it's about the same as x on the outside. Since we're going to negative infinity, right, we have to keep this in mind. Sorry, I'm getting it. So as we evaluate this limit, as x approaches negative infinity, we divide by the biggest power of the denominator, but we do it correctly. So we'll take this 3x minus 2, and we'll divide. This is our blue biggest thing. So we're going to divide each of these by x. And here under the radical, I'm going to divide each of these by x squared, because x squared under the radical is the same as x when it's not under the radical. We have to take care of the sign here, though. We have to pay attention to it. That's 3 minus 2 over x over the square root of, and this is still a limit. Don't forget to write your limit. There we go. This is 2 plus 1 over x squared. Now, as x goes to negative infinity, right, this 2 over x will go to 0, because if I have 2 M&Ms and I share them with the entirety of campus, right, everybody gets to sniff M&M dust or something. Like, it's essentially nothing that you get. So this looks like a 3 over the square root of 2. But this is a negative infinity. And if I look at the original function and x is negative, this is definitely going to be a negative. Right? The denominator will always be positive. Take any x and I squared, it's positive, times 2, it's positive, add 1, it's still positive, take the square root, we're cool. But that numerator is going to be negative, and a negative over always positive is going to give us a limit that is negative. Pay attention to which infinity you're looking at. All right, that's all the learning. Let's do some practicing. Again, I find it to be a better habit to rewrite this in terms of a single fraction. Remember, ambulance just slow rolled by my house. That's a little frightening. This is 4x over x plus 3 over x, only because I live in a neighborhood that is surrounded by older people. And that's how I get the 4x plus 3 over x. But now I've written it so that I have the same power in the numerator and denominator. And so if the powers are equal, we get 4. We could also, the limit as x approaches infinity of 4 is 4. The limit as x approaches infinity of 3 over x is 0. 4 plus 0 is 4. We absolutely could do it that way. When we start adding infinities and different things like that, it gets a little weird. So we try not to just go straight into evaluating these. I like to put them in fraction form first. And that's really just my own preference. Work hard, not smart. When I see that the denominator is higher, if I needed to, I could write this as 0x cubed, 2x squared x, and 6x cubed. Really, there's the difference right here. If I look at my leading coefficients being the same, my limit's going to be 0. I see that my powers are the same, so my limit will be the leading coefficients. I see that this x cubed is a higher power than x squared, so I know this is going to infinity. But I pay attention to this negative infinity. Keep in mind that numerator will always, that's a denominator. It's the second time I've done it now. That denominator will always be positive. And this numerator, as x goes to negative infinity, will always be negative. So make sure you get the sign right on your infinity. Pay attention. Think it through. Will my numerator and or denominator be positive or negative in a negative x value situation? Some of these, they really do require a little bit of work. I'm not going to lie to you and tell you they require a lot of work. Let's see. As I'm doing this one, the work I would do, I have my 2x plus 1. And I have my square root of x squared minus x. I remind myself that the square root of x squared is the same as x on the outside. So I divide everything by x. Outside of the radical, I divide everything by x squared. Inside the radical, I will now have 2 plus 1 over x all over the square root of 1 minus 1 over x. Now, as x goes to negative infinity, I forgot to put the negative there. It's definitely a negative. Of this function, we can see we're going to get an answer of 2. All right. As x gets huge, again, 1 over a huge number is 0. 1 over a huge number is 0. So these are irrelevant. 2 over 1. But we're going to negative infinity. Always go back to this original function to make sure you're checking the signs. Again, that denominator never, as x goes to negative infinity, it'll never be negative, right? That radical will always be positive, and that will be negative. So don't forget your signs. Pay attention to plus or minus infinity. All right. Let's give ourselves some room for that last, next to the last one. Again, all right, we have the square root of x squared minus 1 over 2x minus 1. We remind ourselves that the square root of x squared is about the same as x. About the same as x. So inside the radical, I divide by x squared. Outside the radical, I divide by x. When I simplify this, now I'll have the square root of 1 minus 1 over x squared divided by 2 minus 1 over x. Again, negative, right? That denominator is going to be negative. Negative 1/2 should be our limit. All right, make sure you check the sign. Are we going to positive infinity or are we going to negative infinity? It'll make a huge difference as we do these divisions. So now, if we want to find any horizontal asymptotes, that's actually the goal. We want to find the limit as x approaches infinity of x over x squared plus 9. As x goes to infinity, this goes to 0. And as x approaches negative infinity of x over x squared plus 9, we also get 0. So y equals 0 is the horizontal asymptote. And we can check it out because, you know, we're curious people. X divided by x squared plus 9 Take a look at the graph. Ooh, that's ugly. Let's go ahead and zoom in. So this graph, if we were to blow it up a bit, looks like this. That's it. It's coming back down to 0 out here. It's coming back to 0 out here. It looks like we'll have a critical point. It looks like we might have a maximum or a minimum over here at some point. So there's some work that we could do to it with our derivatives and all, but as far as asymptotes, we got them. Don't overthink it. Do not overthink it. Remember, let me throw down this fact so you can stare at it. I'll even make it in red. It's actually a theorem in our book somewhere that the limit as x approaches positive or negative infinity of 1 over x to the n equals 0. If you have one bottle of Cuervo, one bag of M&Ms, one whatever, $1 million, and you wanted to share it with an increasing number of people raised to a power, right? You essentially get none of that. So that's it. That's the limit.